So we've seen that the ensemble average, or rather the first moment, let us write down the first moment. So the first moment is defined as u x comma t, and it is defined as 1 by n summation n equal to 1 to n u of xt for the nth realization. So you sum over all different realizations. Okay, so how does this look? How does this actually look? So you have, suppose you're sitting in a flow, you have an anemometer. So anemometer is something which measures velocity, wind velocity in this case. So you have a time series of velocity for the first realization. Then you do the experiment again at the same conditions. Say you do it on the next day, but the conditions are the same. Suppose this is the decay of velocity near a coast, near a coastal region. So then you do the experiment again tomorrow, assuming that the conditions are not too different. So then you obtain something like this. Then you repeat it. So you get various time series. So then you basically at all, so this is at a given x. Okay, so this particular average is summed over all the different processes, or the all the different samples, and then you divide it by the total number of readings. So the important thing is that the conditions should be same. The conditions under which the time series is taken, and obviously it should be the same, because if it is not the same, there is no point in averaging it. You're trying to find out average quantity, and unless they correspond to the same physical process. Okay, so of course there will be different fluctuations, but more or less the boundary conditions or the initial conditions have to be same. So another thing about this time series, if you have a time series, okay, so the fluctuations are varying along, so this time scale, so this is time, so this is the time scale over which fluctuations happen. Okay, this is the time scale over which fluctuations happen. This, so it's more or less some time scale. So let us call it as, say, tf, and we see that the overall behavior, it sort of decays over this particular time scale. So t of the macroscopic behavior. So if we choose a window of averaging which is larger than the fluctuation time scale, so let us call this as TA. So this is averaging window. So if this is large enough so that it contains enough fluctuations, but it is small enough than the microscopic time scale, so then when we average this, we will obtain the macroscopic average. So this will be u bar at x as a function of time, and this is true for a non-stationary process because overall it has a time variation. So this is for a non-stationary process. So even for a non-stationary process, it is the choice of TA. So TA must be smaller than, actually much smaller than the macroscopic time scale, and should be much larger than the fluctuation time scale. Only then are you able to smoothen out the fluctuation without losing macroscopic information. Let us look at an example of this. Let us look at an example. So consider the velocity field u t, and let us construct a synthetic velocity field. So this is synthetic in the sense that we will have some macroscopic decay and some fluctuation. So let it be defined as a e raised to minus t upon tau plus b cos omega t. So essentially it's a curve which will look something, so there will be a net behavior like this, but you expect a cosine on this. Okay, so the question is, what is the averaging window which preserves the macroscopic behavior? And we know from intuition that this is the condition it should satisfy. But can we show it mathematically? So let us find the average. So this will be 1 upon Ta integral of t minus Ta by 2 t plus Ta by 2 u t dt. So this will be integral, so this is 1 upon Ta, so t minus Ta by 2 t plus Ta by 2 a e raised to minus t by tau dt plus 1 over Ta integral t minus Ta by 2 t plus Ta by 2 b cos omega t dt. And so this turns out to be 1 by Ta a, so this is e raised to minus t by tau upon minus 1 by tau, and t goes from t minus Ta by 2 to t plus Ta by 2, and this is 1 over Ta, rather b over Ta sine omega t going from t minus Ta by 2 to t plus Ta by 2. So this is minus a tau upon Ta exponential of minus Ta plus minus t plus Ta upon 2 upon tau minus of exponential of minus of t minus Ta upon 2 upon tau plus b upon Ta sine omega t plus Ta upon 2 minus sine omega t minus Ta upon 2. So if you simplify, this becomes a e raised to minus t upon tau sin h of Ta upon 2 tau divided by Ta upon 2 tau plus b cos omega t times sin omega Ta upon 2 divided by omega Ta upon 2. So with the help of some simplification, you will arrive at this particular result. So what does this imply? So from this particular term, if TA goes to 0, then this particular term will vanish. Okay, and this will become 0. No, this will become 1. In fact, this sin h x upon x, so this limit will become 1, and as TA tends to 0, this particular term also becomes 1. So we obtain a e raised to minus t upon tau plus v cos omega t. So we get nothing new. So if the this is quite obvious. I mean, this particular result should not come as a surprise, that if your averaging window is so small that again you're resolving everything, each and everything that is there in the function, then you will get the same function. Okay, you're actually doing nothing, just wasting time. But in fact, if we have the other condition, so let me just write down the expression. So if TA is much smaller than tau, right, then this particular expression, it becomes 1. So then we obtain a e raised to minus t upon tau. But what about this? TA should be much less than tau, and if over here we have omega TA much larger than 1, then because this sine function is always bounded between 0 minus 1 and 1, this particular term being large, this entire term becomes 0. So this entire expression finally boils down to only this expression. So this is the condition that needs to be satisfied. So TA much less than tau, and this implies TA should be much larger than 1 upon omega. And 1 upon omega is sort of the fluctuation time. Okay, 1 upon omega is the characteristic time of fluctuation, and tau is like the decay time of the exponential, which is the macroscopic behavior. So we ultimately arrive at a mathematical constraint which will help us find the appropriate average. We can perform the computations using Python, and we can actually plot everything. Let's see how it looks.